Okay, uh, we were discussing analog communication systems in the previous classes. So far we have discussed is amplitude modulation and angle modulation, which involves frequency modulation and then phase modulation. In the amplitude modulation, we have discussed different modulation techniques, DSB-SC, which is double sideband suppressed carrier, which is simply MT cos omega naught t. So you embed the message information in the amplitude of the carrier. We get it as double sideband suppressed carrier, because in the frequency domain we have seen that you get two sidebands. The spectrum of the message signal gets shifted at omega c and at minus omega c. Accordingly, you have a lower sideband and then you have a upper sideband. Okay, and then we have added a pure carriers with the two sidebands. We name it as AM signal. And then we have also discussed single sideband modulation techniques, in which you suppress one of the sidebands and you just transmit either the upper sideband or the lower sideband. And then we have also discussed VSB modulation, vestigial sideband modulation. Similarly, in the frequency and the phase modulation, you vary the frequency or the phase of the carrier according to the amplitude of the message signal. Okay, so FM signal, we have defined it as phi FMT as A cos omega ct plus kf integral of m alpha d alpha. Likewise, we have a well-defined relation for PM signal. Okay, so all the modulation techniques that we have discussed so far, they have a well-defined mathematical relationship, or you can express all the modulated signals using a well-defined mathematical relationships. And then we have seen the circuits, how you can generate and then how you can demodulate the message signal from the modulated signal. So in all these signals, the signals that we generally have is basically a form of deterministic signal, in which you have information about the signal at each and every instant of time. Okay, so at every instant of time t, you can find what is the amplitude of the signal. Okay, because once you express the signal in terms of mathematical relationships, either analytically or graphically, definitely at each instant of time you can have information about the signal statistics. Okay. But when it comes to the random signals or random process, they are basically not you cannot predict the nature of these signals unless and until the signal really evolves in time. Okay, so the noise in the communication systems is basically an example of the random signal or the random process. So you have a transmitter, you transmit a signal through a channel, communication channel, that may be wired or wireless, and the noise gets added to the channel. So at the receiver, you have to design the receiver in an optimum way so that the effect of the channel noise is somehow neutralized. Okay, and the noise that generally corrupts the information bearing signal which you are transmitting to the channel is of random nature. Okay, so that is why the study of random process is crucial in the design of communication system. And to study the theory of, or to understand the theory of random process, you need to understand the theory behind random variables, because Random process is nothing but it is extension of random variables, and to understand random variables you must understand the basics of probability theory. Okay, theory of probability. Although the probability theory is a very basic thing that most of you understands, or you might have studied these topics, random variables or random process, in the mathematics also, but we will see that how these concepts are used in the estimation of channel noise and in the performance analysis of the communication system in the presence of channel noise. Okay, so if you see probability, so the theory of probability, you generally define an experiment, and related with this experiment you have a sample space S. Sample space S is the outcome of all the possible, is a set of all the possible outcomes of that experiment. Okay, and the term experiment itself, which is used in the probability theory, is to describe a process whose outcome cannot be fully predicted. Okay, like suppose if you toss a coin, the outcome can be head or tail, but you cannot exactly predict whether head is going to appear or the tail is going to appear. And even if you want to go for the exact analysis, okay, then you need so many, you need to know about so many conditions, like what is the angle at which the coin is thrown, and what is the nature of the surface on which it is thrown, the force that is imparted on the coin, and so on. Okay, so the exact analysis is very complicated, so that is why we study the average characteristics in the theory of probability. So you have a sample space now S. The sample space is the set of all the possible outcomes of the experiment. Okay, so if you suppose simply take an experiment of a rolling of a die, the outcome can be 1, 2, 3, 4, 5 or 6. Any one of these numbers it can appear, right? So in the sample space S, you basically have 6 possible outcomes. Okay, I can say this is zeta 1, zeta 2, zeta 3, zeta 4, zeta 5 and zeta 6. Okay, where zeta I, the subscript I, it denotes that which number is going to appear on the dice. Okay, and then we define a event. Okay, so event is basically nothing but it is a subset of sample space S. Okay, like suppose I define an event A where the outcome of the dice is an even number. So this is an event A naught. Definitely A naught is a subset of S. Okay, or we can define another event like this. This is suppose is event A where the outcome of the dice is an even number. Okay, so again A is a subset of S. Or even I can say that I can define a event maybe like this. This is the event suppose B where the outcome of the experiment is a number which is less than or equal to 4. Okay, again B is a subset of sample spaces. So all of these are called as zeta 1, zeta 2, zeta 3, zeta 4, zeta 5, zeta 6, which are basically the values 1, 2 up to 6. They are elementary events. Okay, and if you take the union of all these elementary events, you get the entire sample space, and this event is a subset of the sample space. Okay, now when you define the probability of this event A, probability of any event A is basically NA divided by N, limit N approaches to infinity. Okay, so N is the number of trials. Okay, number of times you have conducted this experiment, and NA is the number of times this event A occurs. Okay, so the probability of this event A is simply the number of times the event occurs divided by the total number of trials, with the condition that is N is sufficiently large. Theoretically, N approaches infinity. Okay, this is what we define the probability of an event A. Okay, and this event A itself may be a elementary event, that means a single outcome of the sample space, like this. Okay, so like suppose if you toss a coin, the outcome can be head or tail. So in the sample space S, you have two possible outcomes, head or tail, right? So these two are the elementary events. So probability of head will be equal to probability of tail. In this case, that will become half. Okay, because if you repeat these experiments over and over again, so you can expect that half of the times head is going to occur and half of the times tail is going to appear. So the probability of head and tail in this case is same, that is 1 by 2. Okay, and if you see this experiment of rolling the die, where in the sample space you have 6 elementary points, and if you see the probability of zeta 1, that must be equal to the probability of zeta 2 and so on is equal to probability of zeta 6. This must be 1 by 6. Okay, we assume that the experiment is unbiased, so the probability of occurrence of each is same. Okay, and if you define certain events, like the probability of this event A naught, this is the event A naught, this is the probability of individual outcomes. Okay, elementary outcomes, and if I say A naught is nothing but the union of these three events, zeta 1 union zeta 2 union zeta 3 union zeta 5, and the probability of this is 1 by 6, the probability of this is also 1 by 6, the probability of this is also 1 by 6. So the probability of A naught will be basically 1 by 6 plus 1 by 6 plus 1 by 6. Okay, so probability of event A naught is going to be probability of zeta 1 plus probability of zeta 3 plus probability of zeta 5, and that will be equal to 3 by 6, which makes it as 1 by 2. Okay, likewise you can define the probability of event AE will also become 1 by 2 and so on. Okay, And you can also define the union of the two events, the probability of the union of two events, A union B. If you have two events A and B, now suppose this event A, this occurs NA times, and this event B occurs NB times respectively. Okay, and if A and B, they are mutually exclusive, or we call it as disjoint, that is A intersection B is basically empty set phi. Okay, that is, they don't have any common point. These two events which satisfy this condition, that their intersection is empty, that means they don't have any common elements, we call them as disjoint events, or we also call them as mutually exclusive events. Okay, like we have defined here two events. One was this A naught, one was AE. So if we take the intersection of AE and A naught, definitely it is an empty set, it is phi. Okay, because if the event A naught occurs, then at the same time event E naught cannot occur. Okay, either the number can be even or odd, they cannot appear at the same time. So that is why their intersection is phi. So if A and B, they are disjoint events or they are mutually exclusive events, and you are trying to find the probability of A union B, then the probability of A union B will be simply the probability of A union B will be limit n approaches to infinity NA plus NB divided by n. Okay, because NA is the number of times event A occurs, NB is the number of times event B occurs. Okay, so A union B, it occurs NA plus NB times because they are mutually exclusive or they are disjoint. So if NA occurs, then NB cannot occur, and if NB occurs, then NA is not present. Okay, means if A is present, then B is not present, and when B is present, A is not present. Okay, so the total number of times A union B is present is the sum of these two, and that is nothing but the probability of A event A plus probability of event B, with the condition that A intersection B is empty. Okay, so you can extend this result and you can generalize it, that probability of union of AI or I will be equal to sum of the probabilities of AI over I, with the condition that AI and AJ, it forms a disjoint event for I not equal to J. Okay, so if all the events are mutually exclusive or they are disjoint, then the probability of the union of all these events is equal to the sum of their individual probabilities. Okay, so likewise, if you say that from this, you can say that the probability of the sample space, entire sample space, is going to be 1. Okay, because if an experiment is repeated n times and n is very large, and S is basically the union of all the possible outcomes. Okay, this is the union of all possible outcomes. So S occurs in every trial. Okay, hence n out of n trials they lead to S, so the probability of S is 1. Okay, because like suppose if you roll a die, then you have zeta 1, zeta 2 up to zeta 6. Okay, and if you see S, the sample space, that is nothing but zeta 1 union zeta 2 union zeta 3 up to union of zeta 6. And all these zeta 1, zeta 2 up to zeta 6, they are elementary events. By default, they are disjoint. Okay, because if zeta 1 occurs, then zeta 2 cannot occur. If zeta 2 occurs, then zeta 3 cannot occur. Okay, so their intersection, zeta 1 intersection zeta 2 intersection zeta 3 intersection so on up to zeta 6, that makes a empty set. So the probability of this S is nothing, the probability of this plus the probability of this and so on up to probability of this, and the probability of each elementary event in this case is 1 by 6. So probability of sample space will be 1 by 6 plus 1 by 6 plus so on up to 6 times 1 by 6, which makes it as 1. Okay, now just to elaborate it further, suppose two dice are thrown. Okay, two dice are thrown. Determine the probability that the sum on the dice is 7. Okay, so when you throw two dice simultaneously, the sample space, you have 36 possible outcomes. Okay, because of one dice it can be 1, another dice it can also be 1. Okay, it can be 1 on the another dice and 2 on the another. Similarly 1 and 3, 1 and 4, 1 and 5, 1 and 6. Likewise it can be 2, 1 and so on. So you have 36. So your sample space contains 36 outcomes, 36 possible outcomes, and all the outcomes are equally likely. So the probability of each outcome, will be 1 by 36. Okay, and the probability that sum is 7, you have to simply look for those points which makes the sum as 7. So it can be like 1 6 or 6 1, one combination. It can be 2 5 or 5 2, or it can be 3 4 and 4 3. Okay, so you have to add their individual probabilities, that what is be given the probability that sum is 7. That is 1 by 36 plus 1 by 36 plus 1 by 36, so on 6 times. You will get a probability as 6 by 36, which will make it as 1 by 6. Okay, so likewise you can have different examples on the probability. These are something very basic. Okay, and then we define conditional probabilities. Conditional probability and independent events. Okay, in the conditional probability, you have two events. Okay, and it may be possible that the probability of one event is affected by the outcome of another event, or it is influenced by the outcome of another event. Okay, suppose you take example of drawing two cards in succession from a deck. Okay, so you have a deck which basically has total of 52 cards, and you draw two cards successfully or two cards in succession. It means you draw one card and then you draw another card. Okay, so let us define A as an event that the first card drawn is an ace. The first card is ace. And if you don't replace the first card drawn during the first try, okay, and let B be the event that the second card drawn is also ace. So you can see that the probability of drawing an ace in the second trial will be affected by the outcome of the first draw. Okay, if the first draw does not result in an ace, the probability of obtaining an ace in the second trial, it becomes 4 by 51. Okay, otherwise it was 4 by 52. In the first case, the probability of drawing the first card is an ace is 4 by 52, because we have 52 cards total and we have 4 cards which belong to this. Okay, so the probability that the first card is ace is 4 by 52. But in the second case, when which I defined as event B, the probability can either be 4 by 51 or it can be 4 by 52. 4 by 52 if I replace the first card after drawing. Okay, if I replace the first card before drawing it second time, then the probability of B will not be affected by the probability of A. Okay, but if I don't replace the first card and I draw another card, then the probability of getting the ace in the second row becomes 4 by 51. Okay, so the probability of event B depends upon whether event A occurs or not. Okay, and this is 4 by 51 only if the probability is only the probability if you are sure that in the first draw the card that you have drawn is not a ace. If suppose in the first card, within the first draw, the card that is withdrawn is an ace, then the probability of the ace in the second card will be 3 by 51. Okay, because event A has already happened. So this is how we introduce the conditional probability. Okay, and the same thing that we will extend to random variables. The conditional probability is denoted with conditional probability is probability of B given A has occurred. So this is the notation, and we read it as probability of B given A. Okay, that is what will be the probability of event B given that event A has occurred. Okay, like what is the probability of drawing the second ace, the ace in the second draw, given that the first is happened. Okay, so there are different cases. So definitely the probability of drawing an ace in the first is 4 by 52. The probability of drawing an ace in the second draw will depend upon whether event A has happened or not. Okay, if it is, if in the first draw the outcome is not ace and you are not replacing that card, then the outcome is 4 by 51. Okay, and if event A has occurred, that in the first draw the card that you had drawn is already an ace, then the probability of B, event B, that means drawing the of ace in the second row, will be then 3 by 51. Okay, so these are the conditional probabilities where one, the outcome of one, the probability of one event is affected by the outcome of another. Okay, now you can express the conditional probabilities in terms of the probability of the event A and probability of event B. Suppose you have n trials, let there be n trials of an experiment, okay, in which event A occurs n1 times, out of which event B occurs n2 times. Okay, so you have total n trials of the experiment and we define a event A which is occurring n1 times, and out of these n1 times event B is occurring n2 times. Okay, so it is clear that n2, which is the number of times the joint event occurs, that is the probability of A intersection B, will be limit n approaches to infinity n2 divided by n. Okay, because out of the n trials event A is appearing n1 times, and out of these n1 times your event B occurs n2 times. Okay, so basically n2 is the number of times that joint event, which is A intersection B, occurs. Okay, suppose we have conducted experiment maybe 100 times. Okay, and out of 100 times, suppose event A occurs 60 times, and out of these 60 times event B occurs 20 times. It means 20 times event A and B, they combinedly, okay, or if you take their intersection, that is 20. Okay, so probability of A intersection B, which is a joint event, that is limit n approaches to infinity n2 by n1. So n2 is out of n1. Okay, so n1 n2 basically gives the probability of the joint event, and this I can write as limit n approaches to infinity n1 by n into n2 by n1. I can modify this equation like this. Now if you look to this equation, limit n tends to infinity n1 by n, that gives you the probability of A, because n1 is the number of times event A occurs. Okay, and limit n approaches to infinity n2 by n1, this gives you probability of B given event A has occurred. Okay, because B occurs n2 out of n1 times that A has occurred. Okay, so event A occurs n1 times, and out of those n1 times event B occurs n2 times. So this ratio n2 by n1, this shows the conditional probability of event B given event A has occurred. That is what is the conditional probability. Okay, So accordingly, I can write this equation as this probability of A intersection B, which is given by this relation. It can be written as probability of A multiplied with probability of B given A. Okay. So from this you can find the probability of B given A. Therefore, probability of B given A is nothing but probability of A intersection B divided by probability of A. Okay. With the condition that probability of A, of course, is greater than 0, otherwise it cannot be defined. Okay. So using a similar, you can say, argument, you can define that probability of A given B will be equal to probability of A intersection B divided by probability of B. Okay. And by combining these two equations, you can also write like, because probability of now A intersection B is probability of A into probability of B given A. So probability of A given B, which is equal to probability of A intersection B over this can be replaced by this relation also. Okay. So I can write it as probability of A into probability of B given A divided by probability of B. This is the probability of A given B. Okay. So this is basically an equation in which you write the probability of the conditional probability of one event in terms of the reversed conditional probability. Okay. So probability of A given B in terms of the probability of B given A. Likewise, you can have probability of B given A as probability of B into probability of A given B divided by probability of A. Okay. So this is what is called as the conditional probability. Okay. So in the conditional probability, you basically have two events, and the outcome of one event may be affected by the another event. Okay. So that depends the conditional probability. That probability of event B given that event A has occurred. So that is probability of A intersection B divided by probability of, we call these as the Bayes rules. Okay. These are very fundamental and very important rules which are used in the probability theory. Okay.